أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم السلام عليكم ورحمة الله وبركاته. Thanks to Allah subhanahu wa ta'ala who has given us one more day, one more chance to repent to Allah subhanahu wa ta'ala. Imagine how many people slept last night but could not wake up. So this is the sole mercy of Allah subhanahu wa ta'ala who has given us one more day, one more chance to repent to Allah subhanahu wa ta'ala. He's been very, very kind, very, very merciful. He has blessed us with countless blessings. If we look around, everything been created directly or indirectly for the services of the mankind. What we have been created for, Allah subhanahu wa ta'ala states in the Holy Quran, more or less meaning, I have created the mankind and the jinn only for my worship. Know how to worship to Allah subhanahu wa ta'ala, how to be a thankful slave to Allah subhanahu wa ta'ala. He sent Anbiya alayhi salam to guide the humanity so that each and every mankind could be successful, not only in this life but the life hereafter. So all we need to follow the commandments of Allah subhanahu wa ta'ala, the way shown by the Prophet sallallahu alayhi wa sallam to get the real success, the success of this life as well as the life hereafter. So inshallah, learning, talking and propagating it will be very, very beneficial for all of us. Today we are going to talk about Fourier series and we'll try to wind up today. If you remember what we have discussed so far, we got an idea about the Fourier series. How do we look into the implementation based upon the configuration, based upon the description, you name it. What is the fundamental or basic constraint behind the scene that has to be fulfilled? We say that the function has to be periodic. If it is periodic with certain period, means we have the repetition over there, we can get into the infinite geometric series form solution. Solution is going to be within finally many terms, since the pattern is going to be of geometrical, one of the form of the series. So we say that the answer is going to be in terms of geometrical or geometric series within finally many terms. So the function has to be periodic, and we got an idea about the period. What the period is, we see if something is being repeated after a certain positive number, P stands for positive constant over there. If the function is repeated itself over and over again, but there is going to be a certain value of P so that it is going to repeat itself. So we say that it is going to be a period. The smallest value among different values, we say that it is going to be the fundamental period or simply the period of the given function. There could be a chance to have more than one periods. Just like imagine We got a straight line. So we need to cut it down. But how much the length of the straight line to be cut it down if it is parallel to the line x-axis? I mean, finally, many options are there. So we have to observe the least value. We all know about the trigonometric functions, sine, cosine. They are.
Excuse me, sir. Sides are
All right.
not visible.
All right, I look into that. I presume it's visible now. Is it?
Yes, sir. Fine.
All right, thanks. Yep. So very first thing that we need to observe as an exercise corresponding to Fourier series. Few examples are there. That we have to find the least period of the following functions. One function could have more than one periods, remember, because we are looking for the repetition. Geometrically, we see certain portion of the graph is going to repeat itself over and over again. So chances are there we could have more than one periods. The least period is going to be the fundamental period of the function. So we are interested to find the least period. If you look into sine, we know that sine is basically trigonometric function with period as 2 pi because it is going to repeat itself. But what about sine of 2x? If you take sine of x, it's much easier. But when we talk about sine of 2x, how do you get to the period, the least value of a constant number to be added into the original function so that you can get the original function back? You see the repetition over there. So I give you an idea. Like we have sine of 2x, and we know that it is periodic with period 2 pi. So sine is there. So we add two pi in it. So now, if you look into the angle over there, so we could easily take sine of 2 times x plus pi. So this is all because it's a scalar multiple, this whole thing inside the bracket. So we are interested to see that the value of p which repeats the original function or you get the original function back is going to be the period, the least value. So by taking 2 sideways, now we see that yes, if you expand this one by utilizing trigonometric formula, you will see that answer is a 2 sine of 2x. So we see that in this case, pi, not 2 pi, remember, because this is the value, an additional value been added to the angle. So is going to be the period of sine of 2x rather than 2 pi. The period, the least period is going to be pi in this case. So this is all. You will look into the period. There are queries behind the scene, sir. Out of 120 who attend class, 45 are in another meeting of programming fundamentals. Why is that? Because it's a scheduled time for mathematics class. So why they are attending the other class? Screen is being shared. So we are talking about an idea about the answer to question number 1, part 1. So 117, why the people are attending the other course? It should not be there because it's a scheduled class. Anyway, so this is the idea. So this is the idea about question number 1 with part number 1, sine of 2x, pretty much on the same line. You can try and then see what could be the least period of option number 2. Try yourself. I look into the queries in the meanwhile. Try the second option. Cosine 2 pi x upon k. Here you go with the idea. So in the first example, we observe that the period is going to be pi. What could be the period? Slides are not clear. You must have the downloaded file, isn't it? Don't you have? Anyone of you try to think about the previous example, sine of 2x. Cosine is there, cosine. Two pi upon kx. So you have to find the least period of this function. It's a trigonometric function. Cosine of x is there, for example. We know its period is 2 pi. So you take start from that and see what could be done. I give you an idea. Yep, 117. Its period is going to be k. Think about that. Cosine of 2 pi x on k plus 2 pi. So that could be written as, I show you in a minute. Something like that. So eventually you see that anything added to x is going to be k. By taking 2 pi upon k common, it will return you cosine of 2 pi upon k times, 2 pi upon k, this whole thing, multiple of x plus k. So this is how we get an idea about the least period. Finally, Fourier series of the following functions. Second question, f of x is equal to x squared, f of x is equal to x cubed. So interval is given from minus pi to pi. Sometime, yes, we can look into the advantage of the given function being even or odd, but not necessarily every time you have to be given an even or odd function. Sometime it is neither even nor odd. Question number 2, part number 1. Clearly, it is going to be an even function against the interval from minus pi to pi. If you do, when the interval is given, of course, we have to look into that restriction. X is extended from minus pi to pi. So better off to look into the graphical representation. Two versions are there behind the scene. Remember, one is the geometrical aspect. You go and then plot the graph to see whether it is symmetric about the vertical line or symmetric about the origin. So based upon that, you will look into the even or odd function. Second criterion is there. If you replace x by minus x and you get the original function back with positive sign or with a negative sign, based upon this mathematical criterion, we describe whether the function is even or odd. Yes, we can look into the first and second example being even and odd. But if you look into the third example, third part of example number 2, e raised to power x against a specific domain from 0 to 2 pi. So it is neither even nor odd function, because if you look into the plot over the interval from 0 to 2 pi, neither symmetric about the vertical line nor symmetric about the origin. If you replace x by minus x, no idea about the original function to be back, because it is going to be e raised to power minus x in this case. So if this is the case, you have to calculate all the coefficients, a naught, an, and bn. Formulas are there. In all these cases, the period of the function is going to be 2 pi. So how do we observe the period? The final value minus the initial value. So pi minus minus pi, it is going to be 2 pi. Pi minus minus pi, it is going to be 2 pi. 2 pi minus 0, it is going to be 2 pi. So all these functions are periodic with period 2 pi. So better off to describe whether the function is even or odd before we move on, because it will reduce the computational cost significantly. But sometimes, if this is not the case, like in the third part, e raised to power x is neither even nor odd function, so then of course we have to go back and then calculate all the coefficients. For an even function, we know that bn is going to be 0. For an odd function, a naught and an, they are going to be 0. Eventually, different from the previous example. Example number 3. It's opposite to what we have been given in part in question number 2, for example. The mathematical formulation was given. Now we have been given the geometrical aspect. It's a piecewise function. We are having more than one pieces of the function. The function is defined over the interval from minus pi to pi. So this is the least value, and this is going to be the largest value. So final value minus initial value, it is going to be 2 pi. So the function is defined over the interval of 2 pi. But we see it has more than one piece. The very first piece is there from minus pi to 0. When x is greater than minus pi and less than 0, the value of the function is there. And it's pretty clear the value of the function is going to be 0, because on the line x-axis, f of x is going to be 0. And the second subinterval from 0 to pi by 2, the value of the function is 1. And the third subinterval from pi by 2 to pi, the value of the function is going to be minus 1. So this is all. We have been given a piecewise function with 3 pieces over there. Of course, you need to describe whether the function is even or odd. 2 options are there. If it's 1 unit, like in this previous example, sometimes it's much easier to see whether it is even or odd. But if it is piecewise function, the best of the option is the geometrical aspect. So is it symmetric about the vertical line, or is it symmetric about the origin? Think about that. If it is there, of course, you can find the Fourier series by reducing the computation cost. But if it is not there, as I presume, then of course you have to calculate a naught, an, and then bn. Period is a 2 pi. Function is defined over the interval from minus pi to pi. So you have to calculate a naught, an, and then bn. Question number 4, the other way around. The expression is given rather than the geometrical aspect. You see, in question number 3, geometry is given. Now we have been given the expression for a piecewise function. First part of example number 4, we have x and then pi minus x. Against the part of the domain from 0 to pi, the other part of the domain. This is, how a piecewise function is defined. If a portion or a piece of the function, a function is defined against a specific part of the domain, that part of the domain should not be repeated. A different expression should be against different part of the domain. So the first part of the domain is from 0 to pi. The other one is entirely different from this part of the domain. It's from pi to 2 pi. So this is all how we define a piecewise function. Pieces are there. Expression of f of x is x and then pi minus x. So as I said earlier, when it is piecewise function, it's pretty hard. Hardly you can imagine whether it is going to be even or odd. But yes, once you go back and then plot the graph, There you can guess whether it is even or odd. Once it is even, decided whether it is even or odd, then we can take an advantage. If it is not the case, of course, we have to go back and then calculate all the coefficients. Even being an even or odd function give us an advantage to reduce the computation cost. If it is not the case, then of course we have to go back and then look into the fundamental thing. The formula is there with the A naught, AN and BN. So better off to plot all these graphs, their periodic extension, and then calculate the coefficients to describe the answer in the form of series. Number 5, it's different periods. Period is 2L instead of 2 pi. So in all these cases, you see that period is going to be 2 pi. The least value and the largest value is there. 2 pi minus 0 is 2 pi minus 0. So 3 pi by 2 minus pi by 2. So the overall interval is going to be 2 pi. So over here, we see that it's a different case. More general, more open. For any value of L, we have to look into the Fourier series of the following functions. What the length of the interval is there, 2 minus 0, it is 2. So for these cases, we have the expression for the period P is equal to 2L. So plug in P is equal to 2. So here you go with the value of L as 1 from here, because you have to utilize the formula. In the formula, there will be A naught to be calculated, but against the value of L. A naught to be calculated, AN, and then finally BN to be calculated. So all you need to know L. So this is how you calculate L from here. I mean, this is an additional part. Sometimes it's not given. P is equal to L is equal to 2. You have to calculate yourself from here 2 minus 0. So over here, the length of the interval is 4. 2 minus 2, 4. So 2L is equal to 4. Means from here, L is going to be 2. So L is going to be 1 with 2 in this case. And finally, we have a piecewise function. Piecewise function against a period, arbitrary period of 12. So from here, you find the value of L. So 1 by 2 minus 1 by 2, it is going to be 1. So this is all. You see, the function is defined over the interval from minus 1 by 2 to 1 by 2, means of length 1 unit. Number 6, which of the following functions are odd, even, or neither odd nor even? Pretty simple idea, is it? I mean, mathematically, expression is given. So replace x by minus x and then see whether you get the original function back. If it is a, then you have to see whether the sign is positive or negative. Positive means function is even, negative means it is odd. If you don't get the original function back, it means that the function is neither odd nor even. And look into example number 5, for example. Think about that. Give me answer to question number 6, part 5, whether it is even or odd. So 04, yes, it is going to be even. Remember, pretty simple idea. If you are clear about the concept, whatever is there, things are much easier. We know that it's mod function. Whatever the value inside this mod, absolute value is going to be positive value. mod, modulus, absolute value, magnitude, many things you can describe this. So if you replace x by minus x, it will turn out to be minus x cube, but because of this mod, it will be positive value. So this is how we say that it is going to be even. But what about number 6? Sine is odd, cosine is even. So you have to think about that. Combination, I mean, in the form of sum, not the product, remember? Yes, we know that if it is a product, we can easily judge whether it is even or odd, but if it is not the case, no. All right, so next. So taking an idea about these things, 7 are the following functions which are assumed to be periodic of period 2 pi, even, odd, or neither even nor odd. So if the function is given without any restriction, so we can directly look into the mathematical formulation. So better off to look into the mathematical formulation because there is no certain value of x. For what value of x? For any value of x. So this is how we better off to look into the mathematical formulation to describe whether the function is even or odd. So what the mathematical formulation, f of minus x should be equal to f of x, or f of minus x should be equal to minus times f of x. F of x is equal to this one in the first case, second case, third, and then so on. But if the period is given, like in example number 7, part 1, sine x over the interval from minus pi to pi. So you're better off to go into the graph against this period from minus pi to pi. Mod of x is there from minus pi to pi. And then piecewise function is a interval is given from minus pi to 0, it's 0, and from 0 to pi, it is going to be x. You need to see whether it is symmetric about the origin, whether it is symmetric about the vertical line. You can see that it is going to be symmetric about the vertical line, but in that case, I don't think so. So you can try and then see the graphical representation. Find the Fourier series of the following function. Again, you have an expression with two pieces over the interval from minus pi to 0 and then 0 to pi. So better off to judge whether the function is even or odd. So because in this way we can significantly reduce the computational cost. So plot this graph against minus pi to 0 and then from 0 to pi minus x square upon x, and then the x square is there, and then see whether it is symmetric about the origin or vertical line. Pretty much on the same line, you need to go and then plot sine of x, mod of that, because we know that, I mean, sine could be negative at times if the value of x is minus. So yes, we have a portion of the interval from minus pi till 0, before 0, we have all sort of negative values. But because of that mod, it is going to be positive. So interesting example is there. Plot the graph against the interval from minus pi to pi. It is entirely different from f of x equal to sine of x only because of that mod. Next example, number 9, if f of x is equal to x square defined over the interval from 0 to L, then find the half range Fourier cosine series and the half range Fourier sine series. We see that yes, 0 to L is basically half of the range of the length of the periodic function with periodicity 12. So what we see in this case, we have to extend the given function against other half of the interval. We have been given the function is defined against the interval from 0 to L, and we will define or we will extend the given function against the other half of the interval from minus L to 0, so that it is going to be defined over the interval from minus L to L with period 2L, the fundamental thing. Since the function is defined over half of the interval, so we say that it is going to be half range. Eventually, half range Fourier cosine or half range Fourier sine, based upon the idea whether it is going to be even or odd. No matter what the expression is there, you have to make it. You have to make it. For Fourier cosine series, the graph is going to be symmetric about the vertical line, and for Fourier sine, it has to be symmetric about the origin. You have to make it. Sine of x is there. Is the other example. It's defined over the interval from 0 to pi. So what we do, we will extend this given function to the other half of the interval, so that it is going to be defined over the interval from minus pi to pi with period 2 pi. So same idea is it, because the function is defined against half of the interval. So we call it half range Fourier series cosine, because it is going to be symmetric about the vertical line. Even function sine series, because it is going to be symmetric about the origin for an odd function. So you have to make it with the extension. When you plot the graph to the other half, you have to have symmetric about the vertical line for the first part and symmetric about the origin for the second part. All right, so that's it.